Okay, thank you so much for that great workshop, that great conference. I'm sorry for the long title. Um, I would like to thank, of course, the organizer and a special thank to Mahdi here. So I've been working now for several years on Hacking's argument, which he called the experimental argument in favor of scientific realism, because yeah, I think it's a good argument. I think it's better than the competition. It's better than the no miracle argument. But as you know, it leads to a form of extra-galactic anti-realism. And at the same time, I've been also working in the field of philosophy of astrophysics and philosophy of cosmology. So to use an expression that Cathy used this morning, I would like to have some kind of parity between astronomical systems and terrestrial systems. So what I've been doing in experimental argument. So my goal in those paper was just to modify the experimental argument in a way to restore this parity, but I didn't go into the detail of what was the commitment that we have to endorse if we are realist about the astrophysical systems using Hacking's arguments. So that's why I'm going to try to do today. I'm going to address the following question. What kind of realism do we end up with when we modify Hacking's experimental argument to include the possibility of natural experiments? Experiments that don't require any human being acting directly on a system. And do we end up with a kind of realism that is different or similar from Hacking's original entity realism? My outline is the following. I'm going to just to present the Hacking's original argument and some of its problem. Then I'm going to present what is the modification of the argument that I find the nicest. I'm going to focus on two case studies after that from astrophysics and cosmology to try to unpack what is the ontological commitment that we have when we modify Hacking's argument. And I will conclude on the question of entity realism by addressing two very smart remarks by Chakravarti. So first, the original argument of Hacking. So, of course, I think many of you already know this argument. If you read it like that, this argument is not that we infer the reality of electron from our success. We do not make the instruments and then infer the reality of the electron. That gets the time order wrong. By now, we design apparatus relying on a modest number of untruths about electron in order to produce some other phenomenon that we wish to investigate, and we are completely convinced of the reality of electron. When we regularly set out to build and often enough succeed in building new kinds of devices that use various well-understood causal properties of electron to interfere in other more hypothetical parts of nature, you can see that there are a lot of problems here. First paragraph, it's telling you that, oh, no, my argument, my experimental argument is not a success to truth inference. Second paragraph, oh, we need to succeed in building apparatuses and devices pretty often. So what is the role of success? And, oh, my argument is not a theoretical argument. I'm infra-theoretical. Second paragraph, end of the first paragraph, we do need a modest number of untruths. And if you want to know what is an untruth, you can't find a definition in representing and intervening. But there is one thing clear, I think, in that argument. It's not that the argument is not about the reality of what we experiment on, but the reality of what we experiment with, contra what you said, Ken, in your case study. I'm just going to buy it right now. I'm just not going to discuss that. I'm just saying that that's the way the original argument is formulated. So we have several difficulties with this argument that I just showed. First, the problem of success. Is that a success to truth inference or not? The problem of untruth. The problem of untruth is really important because if you say, oh no, I just want a very minimal set of untruths, maybe your argument is going to collapse into purely instrumental view of science. But if you don't circumscribe this untruth, this perimeter of untruth, then your argument, your experimental argument can balloon, can inflate into a full-blown theoretical realism, which is exactly what hacking doesn't want. A third problem, the problem of anthropocentrism. Like the notion of manipulation, of manipulability that we have been discussing here today is an anthropocentric one, at least in its most common sense. If I manipulate something, it's because I am a human being and I'm changing the shape or the place of that stuff. And it's kind of weird that an argument for realism relies on what human being can or cannot do. And finally, there is a problem with non-manipulable entities. The fact that we do have belief, or we do think that some entities that are not manipulable are true. And the problem of parity that I have between terrestrial and astronomical system is a sub-problem of this one. So what kind of modification of hacking's argument can we try to do? My idea was to try to suggest the minimalist modification possible in order to restore the equivalence, to restore the parity between the ontological commitment to astronomical and terrestrial systems, but also that this modification can help solve or at least give some insights into how we are to approach the other problems of hacking's argument. And my solution is, I think, quite simple. It's just to say, okay, we just have to forget about manipulation or to define manipulation as a Woodwardian intervention. So again, I think you may know or not that, but Woodward trying to come up with an interpretation of what does it means that X causes Y has developed this interventionist account of causality, of causal claims. And this interventionist account says that an intervention on X with respect to Y is an exogenous causal process that completely determines the value of X in such a way that if any change occurs in the value of Y, it occurs only in virtues of Y's relationship to X and not in other way. What I mean by that is that an intervention is something that makes the value of an independent variable change, and if you have a causal link between this variable and another one, then only the change made by the intervention into that independent variable should affect the dependent variable. But I'm not here to talk about semantic of causal claims. I'm just using that definition of Woodward as a way to define what is an experimental intervention. So what is an experimentation? So we can be more liberal than Woodward. We can forget about the idea that we are doing that for the purpose of determining whether X causes Y. We can also forget about the claim that the intervention has to be exogenous, but I'm not going to talk about that today. Why can we forget that? Because we only need to know that an intervention is a causal process that puts a system into a specific state. And this specific state gives us epistemic access to investigate a lot of things like causal claims, sure, but also measuring constants, exploring new effects, testing hypotheses. There can be a lot of goals of experimental research. So our definition of intervention should reflect that. What is crucial about Woodward's definition of intervention and what has made me interested in that definition is that Woodward is adamant they have the right causal correlational characteristics. Sorry for that. Apparently, my connection to internet is not stable. Indeed, the important and philosophically neglected category of natural experiment typically involves the occurrence of processes in nature that have blah 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 and that are not that do not involve human action, or at least are not brought by deliberate human design. So here we are. If we need a non-anthropocentric definition of what is an experiment, what is an intervention, we can use Woodward's definition. And it solves the problem of anthropocentrism. It's also, I think, solves the problem of home truth. And I'm going to come back to that later, so I'm just sketching my answer here. So what is an home truth? Well, an home truth is the one we need to qualify X as being an independent variable. That's what you need. Because that's all you need to say, I can intervene on X, and that will have some effect on the system I am experimenting on. It can also lead us to understand better what kind of success Hacking is talking about in his argument. He's not talking about a success to truth inference, which is like, I have this theory T that postulates H, T is successful, therefore H is true. Hacking success is much more a kind of technological success. It's the idea that you have a relation from a causal process to the change of the value of a variable that is robust, that you can use in different contexts. So I would say that if you want to look at the idea of success that is needed in Hacking's argument, it's more close to robustness or to systematicity than to the success, empirical success. And finally, I think that this notion of intervention, when you put it into the experimental argument, it can help solve the problem of extragalactic anti-realism. That's what I'm going to show with two case studies. First from astrophysics and the second one from cosmology. So from astrophysics, the case I'm going to study is the case of strong gravitational lensing. We were talking about that a second ago. Oh, sorry. A strong gravitational lens is when you have a lens, so a massive object, that gives you several images of a background source. So typically, here you have a cluster of galaxies and you have a background galaxy and you observe it with different images that are often really deformed. What is happening here is that the light is coming through different paths, and different paths don't have the same length. So when there is a variation in the source, in the background source, you will see it as an observer with a certain time delay in the different images. That's what happened with this really interesting gravitational lens. There was a supernova in the background galaxy, and the supernova was seen at different moments in the different images of the source. And we can actually predict that it will appear, I think it's in 2032, in the last image of the source. What is interesting is that it has been known since the 60s that the time delay between the different sources, different images of the sources is directly connected to Hubble's parameter, or Hubble's constant, which is the current rate of the expansion of the universe. And you can clearly see here that what you have has exactly the right correlational and causal structure needed for an intervention. You have a variation of the source, which is linked to the variation of the images of the source. And from there, we measure a time delay. But we are not interested in the relation from the variation of the image to the time delay. We are interested in how this time delay is related to Hubble's parameter. So another way of representing that will have to be to put that trouble parameter, like just being the inverse proportionality constant in that relation. So for me, this is a perfectly good example of a natural experiment, and I think it goes against the conclusion that Hacking claimed in his 1989 paper. But I want to give you another example, yeah, I have time, which comes from cosmology, and I need it because it will lead us to be much more deflating about the ontological commitment inside this experimental argument for scientific realism. This is a case that is a bit more convoluted. So let me go step by step. First, during the 60s, particle physicists had a problem that they had no upper limit to the numbers of families of leptons. And there are no upper limit so to the numbers of neutrinos. It was often called the problem of the number of families of neutrinos at the time. They had an idea that there couldn't be more than 15, but they had no good constraint on that number. And at the same time, cosmologists were facing another problem, which is to explain why there is this abundance of helium in the universe. And in 1967, Hoyle and Taylor, in a paper called The Mystery of the Cosmic Helium Abundance, showed that the only way to account for that, for our measured abundance of helium, was the mechanism of a primordial nucleosynthesis. So a nucleosynthesis happening in the universe, in the early universe, in the primordial universe. So actually, because Hoyle was a supporter of the steady-state cosmology, he thought that that could happen in what it called supermassive stars or mini Big Bang, but that's just some historical detail that I'm going to forget about. What is interesting in that in the diagram they showed in their paper, you can clearly see that helium-4, so an isotope of helium, has a specific situation. Helium-4 does not really decrease after it has been produced by the primordial nucleosynthesis. And that's important because a few years later, a Soviet cosmologist connected the idea of the number of families of leptons with the idea of primordial nucleosynthesis. Schwarzman showed that the number of particle types impact the expansion rate of the primordial universe, and therefore the duration of the primordial nucleosynthesis. This moment around 1 minute, 2 minutes after the Big Bang, where you have a density and a temperature that is high enough for having a thermonuclear fusion reaction inside the universe. And all of the pieces came together almost 10 years later, when Gary Steinman, David Schramm, and James Guns put a cosmological limit to the number of massive leptons, because helium-4. But because helium-4 does not decrease, does not really decrease after the primordial nucleosynthesis, the abundance of helium-4 constrains the number of leptons type. So they have this kind of causal reasoning and say, okay, let's imagine that we change the number of families of leptons, that changes the energy density, then the speed of the nucleosynthesis, then the neutron to proton ratio, and then the abundance of helium-4. And they make it really clear that it's some kind of causal reasoning in their paper, because they actually say from the chain, new leptons, increase density, speed up, increase helium-4 abundance, we may obtain an upper limit to the number of unknown leptons. And the number they arrive at is 7. There must be 7 or less families of lepton. Of course, we know that there are only three, so maybe you can think it's not a very good prediction. It's a kind of vague prediction. But at the time, this was a very important work. It was considered as the birth of astroparticles physics, the moment when cosmology and particle physics came together. And for instance, Kama, a famous cosmologist of Cambridge, says in an interview that before this discovery, I don't think that contempt is too strong a word in those early days among physicists. So before that discovery, physicists did not regard really highly cosmology. But that changed bit by bit as a new era came in and particle physics ideas became important. Things changed when, for example, the physicists realized that cosmologists could do much better than the particle physicists as restricting the number of neutrino types. Then the physicists had to admit that maybe the cosmologists have got something. So it was an important moment in the history of cosmology and in the history of particle physics. And why was it an important moment? Not because it was a very impressive prediction, a very dramatic prediction, but because it showed that now the universe could be used as a natural experiment. And that's something that another famous cosmologist, Zeldovich, explained or encapsulated in a motto: the universe is the poor man's accelerator. And I think that it's not just a motto. There is a true analogy here. There's a genuine analogy between the universe and a particle accelerator because they have the same causal or they have analogous causal structures. The intervention, of course, in this case is hypothetical. We can't, we don't have a real variation of the number of leptons. In the case of the strong gravitational lensing, there was a real variation into the source, but not here. But it doesn't matter. You can, a Woodwardian intervention can be a purely hypothetical intervention. That's perfectly okay. That's something that Matthias Frisch shows in his book on causal reasoning in physics. So I think that the primordial nucleosynthesis qualifies as a natural experiment and the universe as a genuine particle accelerator. So we have two examples of natural experiment, one in cosmology and one in astrophysics. And now we can begin to question, so if we apply the experimental argument in favor of scientific realism to that case studies, what do we end up with? What kind of ontological commitment do we end up with? So we begin to walk into the realm of metaphysics, and that's where I collapse usually. So I'm going to try to do my best not to collapse. First option will be to say, okay, we have an intervention on different variables, all of the variables and all of the relations between the variables are true. I think that will be a lot of ontological commitment. You know, most of the scientific realists like to say, oh, I'm just a modest realist. And I always wonder what was a non-modest realist. I think that's that. A non-modest realist will be someone that believes everything that is needed to perform an intervention. So let's skip that. I think that nobody that I know really endorses that view. Another view that is interesting is Woodward's view, but in his 2003 paper, called that instrumental realism. I think he has moved from that now, but it's still interesting to consider. The idea is that you believe in not only the intervention on a variable, but also the relation that between, or the causal relation in the case of Woodward, that you have between your independent variable and the dependent variable that you're measuring or observing. I think it's a perfectly good way to make sense of what scientists think when they perform an intervention. And it's kind of consistent, I think, with the view that Ken has shown us before. But in my previous papers, in 2021 and 2024, I was kind of a radical Hackingian person. So I didn't want to go beyond the idea that we believe in the entities in the tools that we use to experiment on, we do not believe in what we experiment on. So my idea was that, okay, so what we believe in is just the causal process making the intervention on the independent variable, and that's all. The rest is our object of study, and that's not something we believe in. That works pretty well, I guess, with the case of gravitational lensing. That doesn't work at all with the case of the number of families of leptons. Why? Because we don't have any idea what could be a causal process changing the number of families of leptons, at least in our current understanding of physics. So when I was working for that workshop, for that talk, I changed my mind. And I noticed this very weird version that I'm really not sure that I will defend until I go into the grave, but that's the one I will defend today. It's the idea that what we really are committed to when there is an intervention is that one of the variables that we use to describe a system is an independent variable. That's the own truth I was talking about earlier. What does that mean? That means that we know that we can change its value, or there's something that can change its value either hypothetically or concretely. And we also know that changing the value of this variable will change something, will change the value of another variable in the system. But that's all. That's all. It's both more than before, but only a little bit less. So let me just skip that because I want to finish on time. So when we look at natural experiments, what we have is that we have causal models supporting some counterfactual claims. We have some counterfactual dependencies. And that's toward these counterfactual dependencies that we are committed to when we perform an intervention. It has the ability to bend light of the free path of photons. That's in the case of gravitational lensing. And in the case of the universe, we have to believe that some property or cluster of properties of the primordial universe had the ability to generate atomic nuclei. That's not much, but it's something. So you may think, okay, but if that's our ontological commitment, that's not entity realism at all. Because I'm claiming that we have a commitment towards some ability. So maybe it looks like dispositionalism, or maybe it looks like a kind of structural realism. Well, yeah, maybe. I don't know. And I think that we can't know. I don't think that my experimental argument, the way I propose it when we use the Woodwardian notion of intervention, gives us entity realism in a classical sense. I think that's normal because, in a way, let me skip rightly that will be more understandable. In a way, the experimental argument is not a metaphysical argument. It's an epistemological argument, you know? And as Chakravarti was saying, entities and structure, though metaphysically separable, are for us epistemically interwoven and always come as a package. So it's not the role of the experimental realism to unpack that package. That's the role of metaphysicians, maybe armchair metaphysician, but that's not the role of the experimental realism, experimental argument in favor of scientific realism, because this argument is first and foremost a way to make sense of the ontological commitment involved in the practice of science. And it is not supposed to be, I think, the basis for a natural metaphysics of science. Just before I leave, I want to leave on a more optimistic note. So just say quelque chose. You may have had the feeling that I was a kind of hacking fundamentalist, hacking hooligan, because I've been discussing hacking and only hacking. And I know, don't worry, I know there are other forms of experimental or causal realism. And I think they're okay too. Don't worry, I'm a nice guy, I'm tolerant, and I'm and I'm open to pluralism. And I will go even further than that. I think that this pluralism of causal and entity realism, whatever the name you want to use, is necessary to account for another remark that Chakravarti has made. He says, in the science, one finds graded spectra of commitment, and the realist must emulate this. And I think it's perfectly right. There is a ladder of commitment in science. And the fact that we have different forms of causal contact and that we have explored in the realm of the literature of entity realism these different kinds of causal contact, maybe that's something that can help us climb Chakravarti's ladder. And by that, I mean trying to emulate the spectrum of commitment that he was talking about. And we can have this idea that we have different steps, and at each step, we gain more confidence in the existence of an entity or a property or whatever you like. So that's my conclusion. The experimental realist cannot unpack Chakravarti's package, but it can climb, or they can climb, the ladder of Chakravarti. Thank you so much for your attention.